Hello and welcome to our third video on thermodynamics. Today we're going to talk about the zeroth law of thermodynamics and heat transfer. Specifically, you need to be able to state the three laws of thermodynamics. Today we're going to talk about the zeroth law. You're going to need to be able to define thermal equilibrium, identify the three different methods of heat transfer, and calculate the rate of heat transfer by conduction. So first, let's talk about our zeroth law of thermodynamics. The zeroth law comes from the fact that you know that when you put a substance of one temperature into a substance of a different temperature, those two materials will come to a common temperature. For example, if you take a beaker of water, a glass of water, and you put ice cubes in it, the ice cubes will eventually melt as they cool down the liquid in which they're contained. Same thing with hot coals. We take some hot coals and we put them into a beaker of cold water and we put them into an insulated container. We know that eventually these two will reach the same temperature. That is called thermal equilibrium. Thermal equilibrium means that both materials in contact with each other have the same temperature. So that actually comes from the zeroth law of thermodynamics. The zeroth law of thermodynamics say that two objects, when placed in thermal contact, so touching each other, will eventually come to the same temperature. Now, a couple things that you need to know about the transfer of heat, right? Heat is the flow of thermal energy from one substance to another, is that heat always flows from a hot material to a colder material until they come to the same temperature. Now remember, what temperature is a reflection of the kinetic energy of the molecules in the substance. Higher temperatures mean they're moving faster. Colder temperatures mean they're moving slower. So it should make sense to you that these hotter, faster moving molecules are the ones that are going to move more quickly into the area of slower moving molecules, or the colder materials. And then as they bump into each other, as these faster moving molecules bump into these slower moving molecules and collisions happen, some of the energy is transferred from the faster moving molecules to the slower moving molecules, giving them some more energy and speeding them up. So as these faster molecules slow down, they give some energy to these slower molecules, which make them speed up until eventually everything reaches the same temperature, or the same average kinetic energy. So the zeroth law of thermodynamics states this principle, and in fact two objects are in thermal equilibrium until they have, or when they have the same temperature. So thermal equilibrium is two objects with the same temperature. I have a little applet where we can actually observe that. Here we go. So this is a nice little applet where we can do some experiments and observe molecular motions. Alright, so what we're going to see is we're going to have two different chambers when this loads, and each chamber is going to have the same number of molecules in it, 100 molecules here and 100 molecules here. We can see that these molecules are moving faster, right? That means they have more kinetic energy, and therefore that means they must have a higher temperature. And in fact, according to this little thermometer here, the temperature in this chamber is 750 degrees. Over here, our 100 molecules are moving slower, which means they have less kinetic energy, which means that their temperature is lower, and in fact, the temperature in this chamber is 150 degrees. Now, what we're going to do is we're going to open the wall between the chambers, and we're going to see that indeed the faster moving molecules will move into the area of the slower moving molecules, right? Heat transfers from hot to cold, and we will be able to see that because the number of molecules in this chamber is going to increase. A couple things I want you to think about is, what will the equilibrium temperature of the molecules be when they reach? It will not be 750, it'll not be 150, it'll be somewhere in between. And so make an estimation or calculate what you believe that equilibrium temperature to be. The second thing I want you to pay attention to is, how long does this process take? Alright, so let's open the chamber door and see what happens. Notice here the number of molecules is decreasing as the number of molecules in this chamber increases, right? Heat flows from hot to cold. faster moving molecules begin to move into the chamber with the slower moving molecules. As they move into this chamber, they begin to collide with these slower moving molecules. Now notice that this temperature here has gone from 150 to 423 degrees. And over here, this temperature dropped from 750 right now. It's at 470 degrees, 470 degrees. Notice that my number of particles is starting to even out. I have about 109 molecules in here and 86 in there. And these are going to move back and forth until I become more steady in the amount of molecules I have. So we'll give this a couple more seconds to come to equilibrium. Temperature over here is 447 now. Temperature over here is 453. So we're coming to a common temperature. And in fact, if we let this go long enough, if you said that the equilibrium temperature was 450, you would be correct. In fact, because we started with the same number of molecules, the equilibrium temperature is an average of the two. All right, we're going to go to our next experiment. This one is experiment number 4. In experiment number 4, we start with 200 molecules. This is very much like experiment 1 in terms of the temperatures. This chamber is 150, this chamber is 750 degrees, but now I have 200 molecules in this one and only 50 in here. Again, much more kinetic energy here, right? Temperature is much higher, less kinetic energy here, temperature is lower. I'm going to open the chamber doors. 1, do you think that the equilibrium temperature is going to be the same as it was before when we had the 750 and the 150 degrees? Do you think it'll be 450 again? Second of all, do you think the time to reach equilibrium will be faster or slower? All right, let's open the doors and find out. Again, observe the mixing of the molecules. We have the molecules moving from hot to cold here. We are up to about 130 molecules over here and down to about 120 over here. We can see that this temperature has jumped dramatically. It started at 150, we're now at about 580, whereas this one was 750 and it's only dropped to about 670. So obviously our equilibrium temperature is not going to be 450 like it was when we did the first experiment. We are now at 610 degrees over here and 643 over here. Now, if we continue to let this go, we will find out, and we're almost there actually, that our equilibrium temperature is in fact going to be 630 degrees. How do I know that? Well, take a weighted average. If you're in statistics right now, you know how to do weighted averages, but obviously because we had more particles in the warmer chamber than in the colder chamber, the temperature, the average temperature, is going to be much closer to the original temperature of the warmer molecules. So by a weighted average, if we do that, we'll find out we get 630, and you can see that we're pretty much there. This one is 631, and this is 629 now. Oh, we're up to 630 here. This should be getting to 630 shortly. So that didn't take quite as long, right? More particles here, less particles here. So the mixing of the particles caused it to reach thermal equilibrium much quicker. All right, let's talk about the 3 different methods of heat transfer. The first method we're going to talk about is conduction. Conduction is direct contact. It's heating where the process of energy transfer is through direct collisions between molecules. The examples we were just looking at with the applet of the molecules moving, that is conduction. They are actually colliding with each other. If I turn on my hot plate and I put a beaker of water on the hot plate, right, this is direct contact between the substance I'm heating and the heating coils, and that will result in heat transfer through conduction. Actual collisions between molecules in the heating coil with the beaker, and then the beaker with the molecules of water. So anytime that we have heating by contact, then we have heat transfer through conduction. So the medium itself is not moving. It's the collisions, the bumping into each other, the collisions that are actually transferring the energy, heat transfer by conduction. We need to be able to calculate the rate of heat transfer. Rate of heat transfer symbolized by an H. It is the amount of heat in joules divided by the time it takes for that heat to transfer, time in seconds. Now, this is my equation here. The rate of heat transfer is dictated by K, which is called the thermal conductivity constant of a material. Again, it's a property, just like specific heat was a property, and the coefficient of linear and volume expansions were properties, things we could look up. Times the area. So the bigger the area in contact, the quicker that heat is going to transfer. Times the change in temperature, the difference in temperature between the two sides of the material. So the greater the difference in temperature, the faster the heat is going to transfer. And then divided by L, which is actually the thickness of the material. How thick is the material? How far do those molecular collisions have to go in order to have that material transfer heat in a certain period of time? So thermal conductivity, high heat transfer. Area, big area, quick heat transfer. Greater difference in temperature, more heat transfer. And of course, the thicker the material is, the longer it takes for that heat to transfer. Now, thermal conductivity, like I said, is a constant. With thermal conductivities, we want things with high values of thermal conductivity if we want heat to transfer. So that's why pots and pans are made out of metal, because we want them to conduct heat. We want them to transfer heat quickly so we can cook our food. But we don't want our walls of our house or the clothes that we wear when we have to go outside when it's really cold out to be good thermal conductors. We want them to be thermal insulators. Thermal insulators have a low value K. Here is a table of thermal conductivities. Again, you can see that metals have very high thermal conductivities. They're very good conductors of heat. They're good conductors of electricity as well. Whereas one of the best insulators is air. Now that's not moving air, right? If there's wind, then you get air exchange. But air is actually a good insulator, and that's why in winter, when you go outside, you should wear layers. You want to trap your air in between the layers, right? Your air is warm around you. So air is actually a very good insulator, and that's why layers are so good. We're going to do one calculation of rate of heat transfer. Windows, right? Windows, if you go by your house in the winter and you feel by the window it's very cold, these windows, glass is not a very good insulator. It's not a great conductor, but it's not a terrific insulator. Windows have a glass surface area. This one has a surface area of 1.6 times 10 to the third centimeters squared. Its thickness is this really thin piece of glass, 3 millimeters. I want to know the rate of heat transfer by conduction through the pane when the temperature inside is 20 degrees Celsius and outside is 40. So maybe this is a summer problem, right? 40 degrees Celsius is actually quite warm. So that's our first thing. Our second thing is we're going to find out how much heat is that per hour. All right, so our equation for the rate of heat transfer, right, which is the rate of heat per unit time, all right, is a thermal conductivity constant K times the surface area of the window times the change in temperature between the two divided by the thickness of the window. All right, so this is just a matter of plug and chug, making sure we pay attention to units. So the thermal conductivity of glass is 0.84. That's joules over seconds meters degrees Celsius. So when we go to do our area, notice that our area is in centimeters squared. So we're going to have to convert that into meters squared before we can do our calculation. All right, so our area is 1.6 times 10 to the third. Now that's centimeters squared. So that means I'm going to need to convert that into meters squared by dividing by 100 squared. right, centimeters squared per 1 meter squared. It's not 100 centimeters squared in a meter squared, it's actually 100 squared. Our change in temperature, outside it's 40 degrees, inside it's 20 degrees, so my actual delta T, is 20 degrees, and then I need to divide by the thickness. Again, I need to be working in meters. This is in millimeters, so I need to move that decimal over 3 places, and that's 0.003 meters. All right, so now it's just a matter of doing some math, plugging some numbers into your calculator. If you do that correctly, you should get 896 joules per second. So that is the answer to our question in part A. What is the rate of heat transfer? Our second question then is, how much energy is that per hour? Well, that's just a matter of dimensional analysis, right? If we have 896 joules per second, right, then I just have to multiply by how many seconds that is per hour. There are 3,600 seconds in 1 hour. So if I multiply 896 joules per second times 3,600 seconds per hour, I will come up with a very large number, 3,226,000, I think. So I'll just round that to 3.2 times 10 to the 6th joules. That's quite a few joules in a day, in an hour. Think about that in a day. So that's why your glass panes aren't just glass panes. You have multiple panes, usually with a layer of either air or a vacuum, or even another inert gas in between the glass panes to try to help with insulation, because that's a lot of heat loss, or in this case, heat gain inside. There are 2 other methods of heat conduction that we're going to talk about, or heat transfer that we're going to talk about. The first is transfer through convection. Convection is actually the process of heating by the movement of a heated fluid. So if I put my beaker of water on my hot plate, right, I heat the water through conduction, right, direct contact, but then let's say I put something above the water. As this water begins to boil, right, it generates a heated fluid. In the case of steam, so that would be gaseous water, or even just the air around it. It would heat the air around it, molecules in the air, and that would move up, right? As it increases in temperature, it decreases in density, right? It expands, and so it will rise and heat whatever I have above here. So it is the heated fluid that is actually heating the object above. So that is actually convection. So convection is the process of heat transfer through the movement of a heated fluid. Now, as I said, right, as things increase in temperature, they expand, which then will decrease their density, and they will then rise. As they rise, they replace the fluid that's cooler above them, and that fluid then sinks, and we end up with what is called a convection current. When I lived out east, we had heating in our house through a radiator. A radiator was great because it produced a heated fluid, air, and it was moist air, and so that produced these nice convection currents in the house that were moist instead of the forced air that we have here in the Midwest, which produces very dry air, and you have to use a lot of lotion to stay moisturized. Another good example of convection currents actually is if you ever go to a large body of water. Remember that the specific heat of water is very high, so its temperature doesn't change much throughout the day as opposed to the ground next to it. So during the day, the land by the water heats up very quickly, right? So we produce heated fluid, right, warm air that rises, and the air over the water is cooler, so it replaces it. So if you are near the shore here, you will feel a breeze coming off the water. That's actually due to the convection currents with this differential heating between water and land. Now, at night, again, because the specific heat of the ground is much higher than the water, much lower than the water, it will decrease in temperature a lot quicker, and so we end up getting warm air rising over the water, replacing the cold air over the land, and now we get a breeze that goes from the shore onto the water. So the direction of the wind by water-land boundary changes during the day due to these convection currents. The last type of heating is heat transfer through radiation. Radiation is the process of heat transfer by electromagnetic waves. There's no medium required, right? Waves, transverse waves do not need a medium to travel. Electromagnetic waves do not need a medium to travel, right? That's how the sun heats the earth. I have one question for you and then we will be done. Water has a higher specific heat than iron, right? Water, in fact, has the highest specific heat. If we have equal masses of water and iron that are initially in thermal equilibrium, that means they're at the same temperature, correct? If we use the same amount of heat, let's use 30 calories, which of the following statements is going to be true? Will they remain in thermal equilibrium? Will they no longer be in thermal equilibrium, but the iron will be warmer? Will the water be warmer? Or do you not know without knowing the mass or the exact specific heat capacity? Well, if water has a higher specific heat, then for the same amount of energy, right, its temperature is going to change less. Therefore, if you said that the iron is warmer, you are correct, and you remember something from our first lesson on thermodynamics.